Welcome to this first lecture in Module 2 of the course. So we've been looking a lot at structure, kind of how atoms are arranged when they're connected to each other by way of covalent bonds. In this lecture, we're going to start looking at how those molecules start to look in 3 dimensions. And you might be thinking, this is a lot of structure. When are we actually going to get to the chemistry? And the reality is that the structure determines the function, whether that's the simplest of organic molecules all the way up to the most complicated biological molecules. The way that these things are kind of arranged in 3 dimensions dictates so much of their actual function and how they work in the universe that it's important for us to look fundamentally at how, at the smallest levels, looking at just single carbon-carbon bonds, things start to arrange themselves. And so with that, let's start to look at molecular geometry. I'm going to get my screen in front of us. Okay, so we're looking at now molecular geometry. And so what this will eventually lead into, though I'm not sure if it will be in this video, is hybridization. So molecular geometry and hybridization. So molecular geometry, this is the shape of a molecule. Okay, so it's important to note that with many atoms, a molecule can have many geometries. And again, geometries is also just sort of shapes. So, for example, let's look at some simple examples. CO2 comes to mind as kind of a standard first example when you're looking at molecular geometry. When we have CO2, we have a bonding arrangement where a carbon is situated between 2 oxygen atoms, and each of the oxygen atoms has lone pairs of electrons. Now, the way that I've depicted this molecule, I've depicted it fairly accurately in terms of what we can do with ink in a 2-dimensional piece of paper. That is, the carbon actually has a linear geometry. And we'll look at this in more detail, but if you look at the atoms that are actually attached directly to carbon, we have kind of this linear or straight line arrangement of the atoms. Now, the oxygens are a little bit awkward. It turns out that if you look at the actual things that are arranged around the molecule, they are all planar and flat within sort of this, forming this kind of arrangement of 3 flatwise around the oxygen atom. So we would maybe call that sort of arrangement where it's flat and there's 3 of them around the atom to be trigonoplanar. But it turns out, and I'm going to say this several times, we can't see lone pairs of electrons. So oxygen's really only attached to one thing. And when you're only attached to one other atom, the other things that we can see, doesn't matter how many lone pairs that you have no geometry. You need to be at least attached to 2 different things that can be visualized, 2 different atoms. So an example of an oxygen atom that is attached to 2 different atoms would be H2O. Now this is a fairly good depiction of the molecule, though I could be a little bit more clear and precise about my lone pair of electrons. Now, in a previous example, the oxygen-carbon framework formed a line across that central atom. So we said the central atom that was attached to more than one atom, the carbon atom in that case, we said that carbon atom had a linear geometry. Here, we can't draw a straight line without bending it. So for water, as we go from H to O to H, we can't say that that's a linear geometry. Instead, focusing only on the atom that has at least 2 other atoms attached to it, we say the oxygen atom has a bent geometry. Now, similar to the previous example when we were looking at oxygen atoms, any atom in the molecule that doesn't have more than one other atom attached to it, we say has no geometry. Okay, so we've covered 2 different types of molecular geometry. Officially, we call them the linear geometry and the bent geometry. Moving on to CH4, which is an important molecule called methane. At some point, we'll have to actually come up with that name on an exam. Okay, what we say is that the carbon is tetrahedral. Now that is a very important word, tetrahedral. It's a way for us to arrange 4 things around an atom such that everything has maximum spacing. Now what that looks like is we're going to take one of the hydrogens, attach it to a carbon, and then attach it to another hydrogen with a very bent looking geometry. Then we're going to add a wedge, a dark line, to a hydrogen, and then instead of a straight line bond, we're going to add a dash to another hydrogen. Okay, so we say that the yellow, that is a wedged atom, and this other color is a dashed atom. I'll get to what these things mean in a second, but a tetrahedron has 2 lines. Check, check. We have our 2 lines. 1 wedge and 1 dash. So whenever we draw a tetrahedron, we want to include this 1 wedge and 1 dash. I'm going to make my highlighting sort of match that. Okay, so what do the wedges and the dashes mean? So when we have a tetrahedron, I'm going to draw this one much bigger. I have 4 things attached to a central atom. 2 of those things are attached by straight lines. The other 2 are attached by a wedge and a dash. Okay, so what we have here is we have lines, and these lines, I'll go on this side actually, these lines are actually bonds in the plane with the paper. So the piece of paper that I'm drawing on, I mean, I know it's virtual, but you get the idea. The piece of paper that I'm drawing on has bonds that are parallel to it or lined up with it or completely flat. Now, the wedge, which I believe I was showing as yellow previously, the wedge implies that the atom is coming out towards us. The atom is coming out towards us, whereas the dashed atom is going away from us. Okay. So it's kind of like this. So I've got my finger, the wedge is coming out towards you, and the thumb is going away from you. So my thumb is my dash pointing away. My wedge is my finger pointing towards you. Now in reality, from our perspective, those 2 things are directly over top of each other, which makes it difficult to draw. So I'm just going to tilt my molecule just so that I can make it so I can see my wedge and my dash. That's what we're doing with this. We've tilted it slightly, but in reality, we could have those 2 things sit directly on top of each other, and it would actually just look like we only have 3 things attached, right? They're right on top of each other, and then I can't do the straight up line and then straight down line. It starts to lose its effect. What I'll do in the next video is provide a model of the actual molecule. So what we've introduced with the tetrahedron that we didn't need for the linear geometry or the bent geometry is a 3D component. So the wedge and dash provide a sort of perspective or 3D depiction. Now that's great. That's great for a number of reasons. Remember, we're trying to actually depict things that exist in the universe in 3 dimensions, okay? So that's important. These things exist in 3 dimensions. We need to understand their 3-dimensional properties. But we're working on 2-dimensional pieces of paper. Yeah, I can bust out a model kit and I can require everybody else spends $20 in a model kit, but at some point we need to communicate these things quickly and accurately without putting a bunch of plastic pieces together and kind of keeping track of inventory. We can do that with the wedges and the dashes. So wedges and dashes are going to be critically important. They're Kekulé bonds that indicate 2 electrons. So we have 2 electrons in each of these. Just like any other Kekulé drawn covalent bond, it's just that one's sticking out at us and one's pointing away. And to depict that, we just draw them as a wedge or a dash. Okay, now make note, this is not a dash. We do not want to draw that. That's actually a hydrogen bond. So that gets the big X. Okay, what we want is a dash where the dashed lines are moving sort of parallel to the long edges of the hydrogen, maybe. I don't know. I mean, they're just kind of, they're perpendicular to the bond as it would be drawn as a normal Kekulé bond. Okay. Why a tetrahedron? So a tetrahedron is, just a second. Writing, talking, and spelling. Tetrahedron. Okay. Why a tetrahedron? So a tetrahedron is kind of a complicated shape. But what it does is it allows us to spread electrons out as much as possible. Let's remember, electrons are negatively charged particles. When they're in bonds, they're localized to orbitals. We can only put 2 electrons into the orbitals. The reason why we can't put any more is because that's too much negative charge in the same region or volume of space. So what we need to do is spread those things out across several orbitals. So that's why we generally have this rule. We need 2 electrons. And then we put 2 electrons per bond because 1 electron is not strong enough to keep the 2 protons close enough together to have a bond. Okay. So that's what we're trying to do with 2 electron bonds. So we need these 2 electron bonds, but we need these bonds to spread out as much as possible. Let's say we made the picture easy on us. Okay, so here is a 2D, not 3D accurate, but it's a fine Kekulé structure of methane. Okay, the issue with this is if we have methane here, the bond angle is 90 degrees between an H to CH bonds. So we have these two electron bonds that are 90 degrees away from each other. When we spread them out and put them in a tetrahedron, and this is an important note, I'm going to go on to the next page. In a tetrahedron, the bond angle between any 2 atoms, let's put any 2 bonds actually, because there's actually 3 atoms that make a bond. Any 2 bonds is stars around this, smiley faces, rainbows, 109.5. Know this number. Know this number. I realize that me asking you this number this semester doesn't have as many ramifications because you can just look it up, but this is a number you will need to know. 109.5. Okay, so let's revisit the takeaway from all of this. The takeaway is that when 4 atoms are attached to one central atom, and really, let's think about that. How many atoms do we know that we've been working with want to have 4 partners attached to them to fill their octet? Well, it's only carbon. Okay, but only carbon. In this class, carbon's kind of everything in this class. The focus is on carbon. So this is a big deal. When we're going to have 4 things attached, and we'll do it all the time, we'll have 4 things attached. It's really anytime we're using carbon and we don't have double bonds or triple bonds, we're going to have 4 things attached every time we're going to form the central atom, I guess, will form a tetrahedron. Okay, now just to recap, why? Because the electrons spread out as much as possible. That was 109.5 degrees. 9.5 degree bond angle. Okay, just going back. Remember, let me point to it. That depiction of methane is not accurate because if we did it that way, yes, we would have a really flat and easy to draw molecule. And in some cases, we'd have a huge separation. I mean, look at the separation here to here. That's 180 degrees. But there are too many instances where there's 90 degrees. So this isn't an effective approach to drawing methane. Instead, we want to use the tetrahedron because the tetrahedron gets us to the number that everybody's going to want you to know, and that is 109.5 degrees. Okay, so where does this all come from? There's this idea that's a big deal in high school chemistry and general chemistry, and it's called VSEPR. This is the only time I'll ever say this abbreviation. So this is valence shell electron repulsion theory. So you can see kind of valence, shell, electron, and it's pair probably, electron pair repulsion theory. So what this is saying is that covalent bonds maximize distance from other covalent bonds. And that's what we've been trying to emphasize here. So putting 90 degrees separation is not as good as putting 109 degrees separation. And we can go back to the original molecules that we looked at, and we'll do that sort of next time. But suffice it to say, a great takeaway is the idea of the tetrahedron. They have literally journals called the tetrahedron. Now, I tend to draw my tetrahedrons in this light, where I've got my wedge and my dash sort of pointing down and to the right, and then my straight lines. And you could draw it that way, or you could flip it and rotate it. Remember, these are three-dimensional things that exist in a three-dimensional universe. Just make sure you've got two lines and a wedge and a dash. Okay, so they can kind of roll around as things do. Just two lines, one wedge, one dash, and you've got a tetrahedron. Okay, that'll do it for this lecture. We're going to keep moving along with molecular geometry in the next lecture. Yeah, so I'll just leave it there.